Imagine driving through a road tunnel suspended more than a kilometer beneath a Norwegian fjord, surrounded by hundreds of meters of water, yet never touching the seabed. It sounds like science fiction, but Norwegian engineers have seriously studied this idea. Stay with us to see how it could actually work, and subscribe for more incredible engineering stories. Now look at the scale of the problem. The Sognefjord crossing studied by Norwegian engineers is about 3.7 kilometers wide, while the water can reach roughly 1,250 meters deep. A conventional bridge would need enormous foundations and a massive structure. At this depth, engineers had to think of a completely different solution. Norway's western coastline is broken apart by enormous fjords, with steep mountains dropping directly into deep water. For drivers, these natural barriers can mean long ferry crossings and indirect routes. Norway's ferry-free E39 project is exploring ways to replace some of these ferry links with permanent road connections. A conventional bridge normally depends on foundations, piers, or enormous cables. But across an extremely deep fjord, placing supports down to the seabed can become a huge engineering challenge. The deeper the water gets, the more difficult and expensive those foundations become. So engineers began looking for a solution that could cross the water without reaching the bottom. The solution sounds unusual: put the road underwater, but keep the tunnel suspended above the seabed. This is called a submerged floating tunnel. Instead of resting on rock or soil, the structure stays at a controlled depth inside the water, supported by a carefully engineered balance of forces. The key is buoyancy. When a structure is submerged, it displaces water, and the displaced water creates an upward force. Engineers can design the tunnel so this buoyant force works against its weight. The result is a structure with a natural tendency to float, which can then be controlled at the required depth. But if the tunnel naturally wants to float, why doesn't it rise to the surface? Because engineers must control that buoyancy. The proposed system uses structural elements such as pontoons, tension members, and connections to counter the upward force and keep the tunnel at its designed depth. The tunnel is not simply tied down like an object on the seabed. Its entire system must balance several forces at once: gravity, buoyancy, currents, waves, and traffic loads. The engineering challenge is to let the structure move slightly when necessary, while preventing dangerous movement. Buoyancy can keep the tunnel from sinking, but it cannot decide where the tunnel should stay. That is where the stabilization system becomes critical. Vertical tension elements and surface-connected structures can restrain the tunnel, controlling its depth and limiting excessive movement caused by waves and currents. Now comes one of the biggest challenges. The seabed can be roughly 1,250 meters below the surface. Anchoring a massive structure directly to the bottom at that depth would be extremely difficult. This is why a floating tunnel needs a different stabilization strategy from a conventional seabed-supported tunnel. The proposed tunnel would not be a single narrow tube. Engineers studied a design using two parallel road tubes, creating separate spaces for traffic. Connecting the tubes would also provide structural support and could allow emergency movement between them when necessary. Between the two tubes, engineers can add structural bracing at carefully calculated intervals. These connections help the tubes behave as one system instead of two independent structures. In an emergency, some connections could also serve as protected passages between the road tubes. The tunnel wall must handle enormous forces from every direction. Engineers would combine thick reinforced concrete with a dense network of steel reinforcement. Inside a construction facility, workers would first assemble the steel framework, then place concrete around it to create the massive structural shell. The tunnel's curved shape is not just about appearance. An arch allows forces to travel around the structure instead of concentrating them on one flat surface. This helps distribute pressure through the concrete shell, creating a stronger and more efficient form for a massive underwater structure. From the surface, a fjord can look almost perfectly calm, but beneath it, water is constantly moving. Currents push against the tunnel, while waves create changing forces from above. Engineers must calculate these movements carefully so the structure can flex slightly without losing its stability. And there is another problem above the tunnel: ships. Ferries, cargo vessels, and other boats must continue using the fjord safely. By placing the road tunnel far below the surface, the concept creates a large vertical separation between marine traffic and the hidden roadway underneath. The deeper the tunnel goes, the greater the water pressure becomes. At around 1,250 meters below the surface, the surrounding water would exert enormous pressure on every part of the structure. Engineers therefore have to design the shell, joints and seals to survive this extreme underwater environment for decades. Outside the tunnel is an enormous mass of water, but inside, drivers need a completely dry road. That means the structural shell and waterproofing system must create a reliable barrier. Every joint and connection becomes critical, because a small failure deep underwater could be extremely difficult to repair. Deep underwater, the tunnel cannot simply rely on natural airflow. Thousands of vehicles could produce heat and exhaust gases, so a powerful ventilation system would have to continuously move fresh air through the road tubes. Large ducts, fans, and monitoring equipment would become part of the tunnel's hidden machinery. Ventilation becomes even more important during an emergency. Sensors would detect changes in air quality, while fans could control the direction of airflow. The goal is to prevent smoke from spreading uncontrollably and maintain safer conditions for people moving toward protected escape routes. Fire is one of the most serious risks inside any long road tunnel. In a submerged tunnel, emergency systems must work while the entire structure is surrounded by water. Detection sensors, ventilation controls, fire-resistant materials and emergency power would all have to operate together when seconds matter. The two-tube design could provide another important safety feature. At intervals, protected cross-passages could connect the road tubes. If one side became unusable, people could move through these enclosed passages toward the other tube and reach a safer route out of the tunnel. Building the entire tunnel deep underwater would be incredibly difficult. A more practical approach would be to manufacture large sections in a controlled construction facility. Workers could build the steel reinforcement, install embedded systems, pour the concrete and inspect every section before it ever enters the fjord. Once a section passed inspection, it would have to be moved from the construction site to the fjord. Specialized marine equipment and barges could transport these enormous structures. Every movement would be carefully planned because the sections would be extremely heavy, large and difficult to control on water. Getting the sections into the fjord is only half the challenge. They must then be connected into one continuous tunnel. Each joint has to carry structural forces, remain watertight and survive constant movement. Engineers would need extremely precise connection and sealing systems at every meeting point. At this scale, even a small alignment error could create problems along the entire structure. Surveying equipment, positioning sensors, and hydraulic systems would help engineers bring each section into the exact position. Only after the geometry was correct could the permanent connection be secured. After the sections are assembled, the enormous structure must be brought to its designed underwater position. This cannot happen like simply dropping an object into the sea. Buoyancy systems, pontoons, cables and controlled ballast would have to work together to guide the tunnel downward slowly and safely. Once the tunnel reaches its target depth, the permanent stabilization system takes over. Engineers would gradually adjust the tension in the supporting elements until the tunnel reaches the required position. The goal is not to make it completely rigid, but to keep its movement predictable and safely controlled. Before anyone builds a tunnel this ambitious, engineers have to test thousands of possible situations. Powerful computer simulations can recreate waves, currents, traffic loads, water pressure and structural movement. Engineers can then watch the virtual tunnel react to extreme conditions without risking a real structure. Computer models are only part of the process. Engineers can also build scale models and place them inside controlled water testing facilities. By generating waves and currents around the miniature structure, they can measure movement and compare the results with their computer predictions. Even after construction, the engineering challenge would continue. A submerged tunnel would need regular inspections for cracks, corrosion, joint movement and cable damage. Instead of sending people into dangerous underwater conditions whenever possible, engineers could use remotely operated inspection vehicles to examine the structure. The tunnel could also monitor itself. Sensors distributed through the structure could continuously measure vibration, movement, pressure, temperature, and cable tension. Instead of waiting for visible damage, engineers could track tiny changes over time and investigate problems before they become serious. So why don't we already see submerged floating road tunnels around the world? Because the concept combines several difficult engineering problems at once. Deep water structures, buoyancy control, marine construction, extreme loads, fire safety and long-term maintenance would all have to work reliably as one system. And this distinction is important. The Sognefjord submerged floating tunnel is a proposed engineering concept, not a completed tunnel carrying traffic today. Norwegian studies have explored whether the technology could work, but major technical, economic and safety questions still need answers before such a system could become reality. Norway already has extensive experience building road tunnels through solid rock beneath mountains and fjords. These conventional underwater tunnels are very different from a floating tunnel. Instead of hanging in the water, they are excavated through the seabed or surrounding rock and remain supported by the ground. A submerged floating tunnel would be something completely different, a road suspended deep inside the fjord, balanced by buoyancy and controlled by structural systems. Norway has not built the Sognefjord concept, but the research shows how engineers are pushing the limits of underwater transportation. If you want more incredible engineering stories, subscribe and follow the channel.